Hi there. Before I get into the topic for today, I just wanted to clarify something that I talked about in an earlier video. I was making the point that in a chemical reaction between reactants and products, that there are often other processes that occur that um, uh, reduce the amount of products that you actually get. So there are side reactions that can occur. Um, the reaction can be incomplete, so products can do a back reaction back into reactants, and then you can also lose reactants in one way or another. You can also lose product for that matter. But I think I may have overstated things a little bit because although we always have to be mindful of processes like this that can affect the reactions that we do, there are a lot of examples of chemical reactions where these ancillary processes really are minimal, and the reaction is essentially complete, and we don't have other things that are happening. And um, a lot of these reactions, a lot of the reactions that are done in industry or in the laboratory um, are um, either uh, engineered to be very clean in this way, or um, or they're chosen because they are very clean, and you don't get um, side reactions and stuff like that. So we do need to be mindful of ancillary processes that will affect the yield of a reaction. There are certainly a lot of examples of reactions where you do get all of the reactants reacting and forming products. And the two examples that I want to talk about today fall into that category. So the first reaction I want to look at is described in this problem. Hydrogen is produced by the reaction of 118.5 milliliters of a 0.8775 molar solution of H3PO4, according to the following equation. 2 Cr plus 2 H3PO4 goes to 3H2 plus 2 CrPO4, and we want to determine the mass of hydrogen that is produced. So what's happening in this reaction is solid chromium, which is a metal, is um, basically dropped into a solution of phosphoric acid, H3PO4, and when this occurs, the chromium metal dissolves in the phosphoric acid, forming a solution of chromium phosphate, and in the process, bubbles of hydrogen gas are produced. And so we're interested in knowing if we're starting with a certain amount of phosphoric acid solution, we want to know how much hydrogen gas we're getting out of it. And we're going to make a few assumptions before we tackle this problem. And it all boils down to assuming that the phosphoric acid, that all of the phosphoric acid is reacting to produce hydrogen. So specifically, we're assuming that there is plenty of chromium metal around, and that there's enough chromium to react with all of the phosphoric acid. And we're also assuming implicitly that the reaction is complete. In other words, all of the phosphoric acid um, actually does react to form the products. Okay, so with that said, uh, let's look at our specific situation here. So we're given that we're starting with 118.5 milliliters of a 0.8775 molar solution of phosphoric acid. So that's what we're starting with. And then where we want to go is we want to determine the mass of hydrogen gas that is produced. So we want to go from the volume of phosphoric acid solution to the mass of hydrogen gas. And in my little target here, I've got that we're going to compute the mass in grams. We could compute it in kilograms or other units, but grams are often the most convenient mass unit to work with in these calculations. So that's where we're starting, that's where we're going, and the chemical reaction itself provides a connection between the two substances. So it tells us that phosphoric acid is being consumed and hydrogen is being produced. And looking at the coefficients of the reaction, it tells us specifically that for every 2 moles of phosphoric acid that react, we get 3 moles of hydrogen. And so that's going to be an important relationship for us to work out this problem. And then in the first step, where we need to go from the volume of phosphoric acid solution to the number of moles, we can work that out if we know the concentration of the phosphoric acid. And we do. It's given to us. It's 0.8775 molar, or 0.8775 moles per liter. And so that tells us that 1 liter of solution contains 0.8775 moles of solute, the phosphoric acid. And so that is, we're going to need that to go between the volume and the number of moles. We can see that we are going to have to be a little careful here, because the concentration of the solution is in moles per liter, and the volume that we're given is milliliters. So we are going to have to do a conversion between milliliters and liters, but that's not a big deal. We can do that when we do the calculation. And then the last piece of the puzzle is we're going to need to convert from moles of hydrogen to grams of hydrogen. And that's easy enough. We can do that using the molar mass of H2. So 2 times 1.008 grams per mole gives 2.016 grams per mole. So in other words, 1 mole of hydrogen gas has a mass of 2.016 grams. So now we've got all the pieces to the puzzle, and we can set up our calculation. So we're given that we have 118.5 milliliters of aqueous H3PO4, and we want to start by converting that volume from milliliters into liters. And the conversion factor there is there's 1,000 milliliters in a liter. And so multiplying this conversion factor will allow us to cancel out milliliters. Then we're going to want to go from liters of solution to moles of phosphoric acid. And so here the relationship that we need is the concentration, and 1 liter of solution is 0.8775 moles of phosphoric acid. And so this will cancel out the liters. Now that we've got moles of phosphoric acid, we want to convert that into moles of hydrogen. And this is where the reaction stoichiometry comes in, that 2 moles of phosphoric acid produce 3 moles of hydrogen. So now moles of phosphoric acid will cancel. And finally, we want to convert from the number of moles of hydrogen to the number of grams of hydrogen. And we just use the molar mass, that 1 mole of hydrogen gas has a mass of 2.016 grams. And so the moles of hydrogen will then cancel. And now we can actually do the calculation. If we type the numbers into our calculator, we find that we end up with a mass of 0.314447 grams. And then we're going to round this off to an appropriate precision. The numbers that went into the calculation, the volume had 4 significant figures. The concentration also had 4 significant figures. The molar mass of hydrogen had 4 significant figures. All of the other numbers in the calculation, the 1s, the 1,000, the 2, and the 3, those are all exact numbers, and so they're not going to affect the precision of our answer. So in this case, we're doing a bunch of multiplying and dividing, and the numbers that will affect our precision all have 4 significant figures, and so we want our answer to also have 4 significant figures, and so we'll round that off to 0.3144 grams of H2. And that's how this problem works out. So the second example that I want to look at today is described by this problem. 20.0 kilograms of acetylene, C2H2, is combusted in an excess of oxygen. The water vapor thus made is condensed and collected, and we want to know what's the volume of water that is produced. and we're told that the density of water is 0.998 grams per milliliter. So before I launch into things, I just want to say a little bit about this reaction. So combustion of acetylene with oxygen is, this is a chemical reaction that is used in welding and in metal cutting torches because it produces extremely high temperatures. And so this is good for cutting through metal or welding two pieces of metal together. And the reaction itself is a reaction between acetylene, C2H2, and oxygen, O2. And when a compound like acetylene combusts, all of the carbon gets converted to carbon dioxide, all the hydrogen gets converted into water, and so our products will be carbon dioxide and water. Now this is an unbalanced chemical equation, and before we can use this for a stoichiometry problem, we are going to need to balance this. So I went ahead and balanced the equation, and what we end up with is 2 moles of acetylene plus 5 moles of oxygen gas will react to produce 4 moles of carbon dioxide and 2 moles of water. And so that is the reaction that we're going to need to use. So the problem tells us that we're starting with 20 kilograms of acetylene, and what we want to find out is the volume of water. I've got this in milliliters. If we end up with a volume in liters, that's fine too. Milliliters are a convenient unit to work with in calculations like this, but we should be prepared to calculate liters if that turns out to be easier. And then the reaction itself shows us how acetylene is converted into water, and so this will allow us to convert moles of acetylene into moles of water. Specifically, 2 moles of acetylene react to produce 2 moles of water, so I can go ahead and put that in. And then looking at the first part of the problem, in order to go from the mass of acetylene to the number of moles of acetylene, we're going to need to know the molar mass, and that is 2 times 12.011 grams per mole plus 2 times 1.008 grams per mole gives us a molar mass of acetylene of 26.038 grams per mole. And so that will allow us to convert from the mass of acetylene to the number of moles. We are going to have to be careful that the mass we were given is in kilograms, and the molar mass is in grams per mole. So we'll have to incorporate that into our calculation, but that's not too hard to do, and we'll remember to put that in. And then going from moles of water to the volume of water, we could do that if we knew the volume of 1 mole of water. And liquid water, 1 mole of liquid water does have a particular volume. We're not given any information about that in this problem. Instead, we're given a value for the density of water. And density will allow us to relate the mass to the volume. So it will allow us to connect the grams of water to the number of milliliters. And specifically, 0.998 grams per milliliter is equivalent to saying that 0.998 grams of water has a volume of 1 milliliter. And so this will allow us to do this conversion. And then to get from moles of water to grams of water, well, there we can just use the molar mass. And for water, the molar mass is, looks like I have a typo there. The molar mass is not 26.038. That was acetylene. Molar mass of water is, I think I got it right on this part. Yeah, 18.015 grams of water. So my apologies for the little goof there, but the number that's written over the arrow here is the correct number of grams in a mole of water. So now we've got our plan for how we're going to do the calculation. Let's go ahead and put this together. So we've got 20 kilograms of C2H2. We need to convert that into grams. Using 1 kilogram is 1,000 grams. Kilograms will cancel. Now we want to go from grams of acetylene to moles. And there we use the molar mass. that 26.038 grams of acetylene is 1 mole of acetylene. Now the grams of acetylene will cancel. Now we want to go from moles of acetylene to moles of water. And here's our stoichiometry. 2 moles of acetylene give us 2 moles of water. So moles of acetylene cancel. Then we can go from moles of water to grams of water. 1 mole of water has a mass of 18.015 grams. So the moles of water will cancel. And then finally, we can go from grams of water to milliliters using the density. 0.998 grams of water has a volume of 1 milliliter. And so the grams will cancel. And when all is said and done, everything is going to cancel out and we'll be left with units of milliliters, which is what we want. And when we put the numbers into the calculator, we find that we have 13,865.2 milliliters. Now we want to round this off. The mass that we started with was given with 3 significant figures. The molar mass of acetylene that we had to work with had 5 significant figures. Molar mass for water also had 5 sig figs, and the density that we were given had 3 sig figs. So, and everything else is an exact quantity. So, of the numbers that are affecting our precision, the least precise values had 3 significant figures, so we'll round off our answer to 3 significant figures. And while I'm doing that, since this is a large number of milliliters, I'm also going to convert that to liters by dividing by 1,000, and so that gives us a final answer of 13.9 liters is the volume of water produced in this case. And that is it for this time around.